What up, chemistry people? Today we are going to be learning about how we can select and apply mathematical routines to mass data to identify or infer the composition of pure substances and or mixtures. College Board went a little crazy on that last one. Basically, we're just going to be performing percent by mass calculations and can you calculate and determine empirical and molecular formulas. Okay, first thing, calculation of percentage by mass composition. In order to determine the percentage by mass of an individual element of the compound, express the mass of each element as a percentage of the total mass of the compound. Okay, for example, if we take a look at a compound with the formula C₂H₄O2, boom. The total mass is 2 times 12.01 plus 4 times 1.008 plus 2 times 16.00 to give us a total mass of 60.05. Now, all of those values come from the periodic table. The 12.01 for your carbon, the 1.008 for your hydrogen, and the 16.00 for your oxygen. And that will give you the total mass of your compound. In order to determine the percentages of each of the elements by mass, again, it's just a matter of taking the part over the whole and multiplying by 100. And so as you look at the example with carbon here, we've taken the 2 carbon atoms, 1, 2, added them together or multiplied 12.01 by 2, divided by the total mass, or here's our total mass of the compound here. And as you can tell sort of visually here, the carbon makes up about 40% of the total mass of the compound. As you look at hydrogen, same thing applies. You're going to take the part that's hydrogen, except this time it's 4 times 1.008 over the mass of the total. Hydrogen makes up only 6.714% of the mass of this compound. And again, it's important to note that although there are more hydrogens, there are 4 of them compared to the 2 carbons, because the hydrogens are so much smaller than the carbon atoms are, they make up far less of the percent by mass than the carbon atoms will. And this also applies then to the oxygen. Notice that although there are 2 oxygen, just like there are 2 carbon, because the oxygen are larger than the carbon, their percent by mass is a little bit larger than the percent by mass of carbon. Oxygen in this example makes up 53.29%. Number 2, all pure compounds have a fixed percentage by mass of each element. So the purity of any given sample can be determined by comparing the percentages by mass. A sample that does not match the percentage by mass of a pure sample is not pure. So if they match, you win. If they don't, not the same. Or it's not pure. Number 3. Empirical formulas then represent the simplest or smallest whole number integer ratio of the atoms of each element in that compound. Number 4, the empirical formula can be calculated from percentage by mass data. Number 1, take the percentage of each element and assume a sample of 100 grams. Number 2, convert the masses per 100 grams of each element to the moles of each element by dividing each element's mass per 100 grams by the corresponding molar mass taken from the periodic table. Number 3, find the ratio of the moles calculated in number 2 above by simply dividing each of the moles by the smallest number of moles. Again, empirical formula is a ratio or comparison. How much of one in moles to how much of another element in moles. Number 4, the results from number 3 above will be in a convenient ratio, and gives the empirical formula. Important things to note, though, that sometimes that ratio includes a decimal fraction, such as 0.5 or 0.33 or 0.250, and so on. Since empirical formula are the simplest whole number ratios, you have to remember to multiply all of the numbers in the ratio by 2, 3, 4, etc., whatever number you need to give you that, turn that decimal into a whole number. for example. And if you're a math genius and recognize the fractional representations of these decimals, for example, 0.5 represents 1/2, or 0.333 represents 1/3, or 0.25 represents 1/4, the number that to multiply each of those numbers in the ratio by is equal to the denominator. So for example, if you had a number that was 0.5 in the ratio, if you multiply by 2, it would get you to a whole number, and so on and so forth for those other decimals. Unlike an empirical formula, which shows the simplest whole number ratio, the molecular formula of a compound shows the exact whole number ratio of the different elements in a compound. It's important to remember that sometimes the empirical formula and the molecular formula can be the same. And just like with the empirical formula, the numbers of each element are recorded using subscripts. To the right of the element symbol, when only one atom is present, the subscript 1 is assumed and is not written. So let's talk about the relationship between empirical and molecular formula. The molecular formula will be some simple integer multiple of the empirical formula. For example, a compound with an empirical formula of CH₂O will have a molecular formula of either CH₂O, which is the same as the empirical formula, or C2H4O2, which is twice that, or C3H6O3, which is 3 times that, and so on, where the empirical formula is multiplied by either the 1, 2, or 3, whatever multiple it is that you're working with. Again, integer multiples here. To establish the correct multiplier, what are you going to multiply the empirical formula by, and therefore determine what the molecular formula is, it is necessary to know the molecular mass of the compound. And oftentimes, most times, this will be given to you in the problem. Okay, and sort of an important distinction here between empirical and molecular formula. Again, empirical is the smallest whole number ratio, while molecular formula represents the actual ratio. So in the example where the empirical formula is CH₂O, as you look at how we have sort of determined the molar mass of CH₂O, which took the 1 carbon plus 2 hydrogen plus 1 oxygen, gives a mass of 30.03. However, if the molecular mass, so the actual mass of the formula, does not match the mass of the empirical formula, it tells us that the molecular formula is different from the empirical formula. And in this case, we're told the molecular mass is 60 grams per mole. And so if you just compare 60 to 30, you recognize the actual formula, 60, is twice as large as the empirical formula, molar mass of 30. So as you think about the actual molecular formula, that 2 is your multiplier, so it's just twice whatever the mass of the empirical, this is what your empirical formula was, to give us C2H4O2, or acetic acid, for the molecular formula of this compound. Molecular. Again, it's just a multiple of CH₂O. And lastly, when 2 entirely different compounds have the same percentage by mass, they will have identical empirical formulas. Again, the same ratio of one element to the next. But because they're different compounds, they will have different molecular formulas. So just something to watch out for. Sometimes we have identical empirical formulas, but different molecular formulas. The last thing I want to mention here is that you can have 2 entirely different compounds that have the same empirical formula. As we look at this, we've got P2O5 on your left and P4O10 on your right. 2 different compounds. But if we were to write the empirical formula for P2O5, we would get P2O5. We can't reduce that any further. But if we were to write the empirical formula for P4O10, we would get P2O5. Because the smallest whole number ratio here of phosphorus to oxygen is 2 to 5. So empirical formulas are the same. Molecular formulas are different. The true formula here is P2O5, here P4O10. Side note, just sort of a visual representation of these 2 different compounds. So haters gonna hate, but